Is this visible?
Yeah, it is visible.
Okay, great.
You can start the recording.
So I'll start. Hello, everyone. On behalf of ISI Bangalore students and researchers, I welcome all of you again to another lecture, and this is the last day of Limit Camp. Today we have with us our speaker, Raghavendra Tripathi. He did his master's from IISc, and then he did PhD from University of Washington, and now he is doing his postdoc in New York University, Abu Dhabi. His work of interest, his area of interest is probability and also analysis. He has been the recipient of multiple awards such as Walter J. Micheli's Grad Fellowship in Mathematics, etc. We are very honored to have him here for his talk titled Statistics of Permutations. Again, everyone, please try to keep your microphone off when you are not asking questions. You can also ask questions in the chat, and this meeting will also be recorded and we'll upload it in our YouTube channel. So if any of you need to refer to it later, please check it out there. Now I'll hand it over to the speaker.
Okay. Thank you, Rinkini. And thank you all for organizing this. I'm really very glad and honored to be talking here. So what I'm going to talk about today is, as you already heard, statistics of random permutation. So let me first emphasize the goal really here is that everything that I'll talk about is fairly standard and fairly basic. So all the terms and terminology you will most likely already know. But if you don't know something, if I say some words that you don't understand, please feel free to stop me. The basic question around which this whole talk will revolve is the following question. The question is, how does a random permutation look like? Okay, so how does a random permutation look like? Now, this question is obviously very vague. There are two things that I need to make sense of. First of all, what do I mean by a random permutation? And secondly, what do I mean by look like? So we will explore these things throughout the talk, but the main emphasis, what I want to do in this talk is emphasize that there are very simple questions that you can ask with the undergraduate background, the things that you have learned, and very simple questions when you start asking questions about random permutations, they lead to extremely deep and extremely rich mathematics. So throughout this talk, we will see some questions and we will see their partial solutions and so on. And on the way, I'll also hint or I'll also describe some of the problems which are actually very recent, some of the problems which are actually still unsolved and so on. So let's get back to this question. A random permutation. For those of you who are familiar with a little bit of probability theory, a random permutation basically would mean that Sn, which is the set of symmetric group on n symbols. So this is a set of all permutations of n. And this is a finite set. We all know that it has factorial n many elements. And you can put a probability distribution, you can put a probability mass function on this set. That will give you, and then you choose a permutation from that probability distribution. In this talk, whenever I say a random permutation, I will always work with uniform random permutation. Uniform random permutation. What it means is that I have a probability P on this set Sn, and the probability that my chosen random permutation is equal to some sigma is 1 over factorial n irrespective of the sigma. So every permutation is equally likely of being chosen. So you don't necessarily have to work with this model. You can choose different models of random permutations, which means you can choose different probability measures, and they are also interesting. But for simplicity, throughout this talk, a random permutation will mean a uniform random permutation. Okay. So that was the first thing. Second thing, what does it mean to say a permutation looking like? So this is a somewhat philosophical or a vague question. And here is one way to make it precise, that typically permutations have some properties. Permutations have some properties. They have lots of properties or attributes. So the kind of properties that I have in mind, just to make it concrete, for example, if I give you a permutation, there is a sign associated with the permutation. So you can talk about the sign of a permutation. This is +1 or -1, depending on whether your permutation sigma is even or it's an odd permutation. Okay. Is everybody familiar with even and odd permutation?
Yes, sir.
If
The
you are
number of transpositions, if the number of transposition is even, then it is even.
correct, yes. Okay, great. So this is one property. There are many other properties or attributes or numbers associated with a permutation. For example, there is an order associated with a permutation. So there is something called order of sigma. And then every permutation you also know, for example, so here is a fact that every permutation can be written as product of disjoint cycles. In more or less a unique way, as a product of disjoint cycles. Okay, so it can be written in as a product of disjoint cycles in more or less unique way. What I mean by that is that this the disjoint cycles that appear in the product, they are unique. Their orders are not unique because disjoint cycles, they commute. So you can put them in any order. So up to their ordering, there is a unique decomposition of every permutation as the product of disjoint cycle. So one of the properties that you can ask about a permutation is how many cycles does it have? Number of cycles in sigma. So this is one property. You can think of, for example, length of longest increasing subsequence. I'll come to what this is. Length of longest increasing subsequence. If you don't like increasing, you can take a decreasing subsequence. Doesn't matter. Okay. So I'll talk about this last property in some detail. So I'll define what this is if you haven't seen it already. But what am I trying to do here is that there are lots of these properties. And when you look at a random permutation, you are typically interested in one of these properties, sometimes more. But for simplicity, let's just say that you pick one of your favorite properties, P. And then when I say what does a random permutation look like, what you are basically interested in is that, let's call these properties P. So what you are interested in is understanding what is the behavior of the random variable P of sigma. Okay. Once again, I'm being a bit vague. What I mean by what is the behavior of random variable P sigma is that, first of all, notice that the properties P that I'm talking about, they are all integer valued or natural number valued. So they give you some number. You feed it a sigma, you feed it a permutation, it gives you a number. So if your sigma is random, then this particular property will give you a random number. So you can ask what is the expected value of this number. So more precisely, the questions that you might be interested in is the expected value of this P sigma. You can ask what is the variance of P sigma, and so on. So more intricate question would be that, can we say something about the distribution of P sigma? All right. And also notice that all these quantities, they will obviously depend on n. Your sigma is coming from this Sn. So if you want, we can put a subscript here n, so that so as to emphasize that this is really coming from Sn. So this will be a number depending on n. These random variables, now you don't have just one random variable, but you have a sequence of random variables. So you can ask more precise things. For example, you can ask, if I subtract off the expectation of this random variable, then now what I have is a mean zero random variable. And if I divide it by the square root of the variance, I now have a random variable which is mean zero and it has variance 1. Now this sequence of random variables, let's call this xn. And one of the questions that people study is, does xn have a limit? And obviously you can then ask much further questions that if it has a limit, what is the limit, and so on and so forth, how fast the convergence happens and so on. Okay, so this is the setup that we will be studying random permutation. We will typically have a property P in mind. And when I say what a permutation looks like, we are basically interested in how does a given property behave. It is fairly possible that you might be interested in 2 properties simultaneously or 3 properties simultaneously. You can do all those kind of things. This is what I mean by what does a random permutation look like. So what we will do throughout this talk is we will look at some of these properties and try and understand how people study these kind of questions and how they are related to other parts of mathematics. So let's start with the simplest example. So our property P that we care about is, let's say, the sine of sigma. So this is my property. So I pick a random permutation and I ask basically this question. What is the probability? Notice that the sine of sigma, or if you want a sigma n, this can take only 2 values. It can take value +1 and it can take value -1. So you might want to understand what is the probability that a randomly chosen permutation has sine +1. This is same as asking how many even permutations are there in Sn. So number of even permutations in Sn, and you divide it by the size of Sn, which we know is factorial n. Similarly, the number of odd permutations. Okay. Now, does anybody know how many even permutations and odd permutations are there in Sn?
Sir, n factorial by 2.
Correct. Okay. So the number of even permutations and the number of odd permutations, they are equal, and each one of them is factorial n over 2. What does this tell us? This tells us that this probability is half. So the sine of sigma n for a random uniform random permutation is a random variable that takes value +1 and -1, each with probability half. Okay. In other words, if you know this term, this is a Rademacher random variable. If you don't know it, think of simply as a Bernoulli random variable. Instead of taking 0, 1 values, it just takes +1 and -1 value. The standard name is Rademacher. So here we have done something interesting. What we have basically found is that sine of sigma n is a Rademacher random variable, but its distribution does not depend on n. So we have determined the exact distribution of the sine of sigma n irrespective of n, and it is always Rademacher random variable, standard Rademacher random variables. Okay, so it takes value +1 and -1 with probability half. If you can determine the exact distribution of a random variable, then the questions like what is its expected value and what is its variance and so on, these questions become easy. So for example, in this case, what will be the expected sign? Anyone? Okay, so the sine of sigma n, it takes value +1 and -1. So we are basically looking at +1 times the probability that sine of sigma n is +1, and plus a -1 times the probability that sine of sigma n is -1. both of these quantities are half, so you basically get a 0. So it's a mean 0 random variable. You can similarly find out the variance, and if you look at this quantity, in fact, if you determine the variance, you will find that the variance is 1. So the expected value of sine sigma is 0. So what you basically get is that sine of sigma n, basically you don't have to subtract off the expectation because the expectation is 0 and the variance is 1. So this normalized quantity always remains a Rademacher random variable. And therefore, you also have answered this question, does xn have a limit? All your xn actually are Rademacher random variable, and therefore, as n goes to infinity, you actually get a Rademacher random variable in the limit. Okay. So this was a very, very simple exercise, very simple example. Now let's go to something a little more interesting. So in the interest of time, I'll directly jump to this example. We'll see how much time it takes, and then maybe if I have time, I'll talk about something more. But I want to really cover this example. So the property of interest here is the length of longest increasing subsequence in a given permutation. So this is our second example, length of longest increasing subsequence. Okay. So this is not very standard, it's not taught in the classes, so I'll explain to you what I mean by this. So take a permutation sigma, and for this example, we will write sigma in the two-line notation. So let's take, for example, some permutation. Let's say 4, 5, 1, 6, 2, maybe 3. Okay. So this is a permutation. When I say this is a permutation, I secretly have in mind that I'm writing it in two-line notation, meaning 1 goes to 4, 2 goes to 5, 3 goes to 1, 4 goes to 6, 5 goes to 2, and 6 goes to 3. Good. Now, an increasing subsequence, so this is my sigma. What is an increasing subsequence in sigma? Is basically precisely you want to find sequence of increasing numbers I1, I2, I3, Ik, such that sigma of I1 or sigma of I1, I2, that is also increasing. Okay, so this we will call an increasing subsequence. So very simply, if you have written your permutation in two-line notation, then you have these bunch of numbers. And what you want to do is that you want to find a sequence of subsequence inside here, which is increasing. So for example, I'll write some examples of the increasing subsequences here. You can start with 4, and then 5, and then 6. This is increasing. You could have started with maybe 1, then you could go to 6. This is another one. You could go to 1, 2, 3. Okay. So these are increasing subsequences. There are many more. You can just do, for example, 4, 5. You could have done 4, 6, and so on. Okay. So these are increasing subsequences in this permutation. Is the idea at least clear that what increasing subsequence means in a permutation? Yes, no, maybe. Okay.
Sir, yeah, but what you referred to, that is I1, I2 or delta I1 or delta I2?
Where here do you mean?
What you can call increasing subsequence.
Yes.
Delta I1, delta I2, yeah, or I1, I2.
So an increasing subsequence is basically sequence or increasing sequence of numbers I1, I2, Ik. So these should be first of all increasing. So you find basically k many numbers which are increasing, but then you also want that when I apply my permutation on these numbers, then they also remain in the increasing order.
Oh, yeah,
Okay.
got it, got it. Okay.
So both the conditions should be there. But that's the benefit of writing it in two-line notation, that as you move from left to right, the fact that you always get I1, I2, Ik, which are increasing, is already there because it's written in two-line notation. So we write 1, 2, 3, 4, 5, 6. So as you move from left to right, all you have to check is that do you get a sequence of numbers or subsequence of numbers that's increasing. Okay, good. Now, obviously, you can similarly define a decreasing sequence. I'll not bother to define it, but you get the idea that this time what you want is that as you move from left to right, so you still want I1, I2, I3, Ik to be increasing, but you want that when I apply the permutation, my permutation reverses this order completely. Okay? So this will be a decreasing subsequence. So for example, in this very same example that we have, a decreasing sequence would be, you can go from 5 to 1, let's say. You can go from 4 to 2. Okay. So these are decreasing subsequences. There are many more. You can go 6 to 3 and so on, right? So if I give you a permutation, you can play around that permutation and you can see how many increasing subsequences are there, how many decreasing subsequences are there, and so on and so forth. Okay. So this is our property. And as I was mentioning earlier, the kind of questions that we will be interested in. So let's call this, yes, before that. So we have many increasing subsequences and we look at the longest increasing subsequence in the length. So for example, in this permutation, we have two longest increasing subsequences and they have length exactly equal to 3, right? So hopefully I have not missed any longer increasing subsequence. So given a permutation sigma, let's call L sigma, or if you want L sigma n, this is the length of the longest increasing subsequence. Now, let me point out that there need not be a unique subsequence of the longest length. For example, here we have two subsequences which have length 3, but we are not interested in counting how many of such sequences or subsequences are there, although that's another property that you might be interested in. But for this example, we only care about the length of this longest increasing subsequence, not how many of them are there. Okay. And then you can ask the following question. What is the probability that length of sigma n is equal to k? Okay. So okay, I don't know what has happened. Okay. So length of sigma n is equal to k. This is same as asking the number of permutations sigma in Sn such that the length of longest increasing subsequence has length k, and you divide it by factorial n. There are factorial n many permutations, right? So there are two ways to look at it. Probabilists will care about this number, and you might actually drop this normalization factorial n from here, and you can simply look at these numbers, counting these numbers, and you can just ask what is the behavior of that sequence of numbers. Okay. So this is our random variable that we are interested in studying. Let's do some very simple example as the sanity check. If I give you a permutation, I ask you how many permutations are there in Sn such that the longest increasing subsequence has length n. Can anybody take a guess, or can anybody give an answer? How many permutations have length of the longest increasing subsequence equal to n?
Sir, 1.
1. Good. Do you know why?
Sir, only one case is possible. That is 1, 2, 3, 4 dot dot n.
Correct.
That is
Okay.
1 goes to 1, 2 goes to 2. The identity.
Exactly. So the identity is the only permutation because you want the length of longest increasing subsequence to be n. So the first number that you need to put here, there must be n minus 1 many numbers bigger than that. The only number that can appear at the first position, therefore, is 1, and so on. You inductively follow it, and you get that identity is the only permutation. And this number, notice, doesn't depend on n. The other extreme, how many permutations sigma in Sn have length of longest increasing subsequence equal to 1? So this time, basically, we don't want any increasing subsequence. In other words, we want our permutation to be strictly decreasing. Can you give an answer in this case?
Sir, 1.
Okay, great. So in this case, we still have 1, and this time your permutation is basically n minus 1, 1. Okay. So great. Now, what is it telling you? That if you pick a permutation uniformly at random, the probability that it has very few increasing subsequences, or the length of longest increasing subsequence, is very small, like 1. That's very rare. It's 1 in factorial n. Similarly, it cannot really have an increasing subsequence of very long length, like n. That's also very rare. It's 1 over factorial n. Now, guess time. If you pick a random permutation, typically, therefore, you see that it should kind of increase and then decrease maybe. So what is the most likely situation? Most of the random permutations, let's say, what is the length of the longest increasing subsequence? Are they generally around, let's say, n by 2, root n, log n, n to the power 1/3, or what? Does anybody want to take a guess?
The floor value of n by 2 something.
Okay, that's a good guess. Turns out, surprisingly though, that that's not the right answer. Okay, and it looks a reasonable answer at first, because it seems like it's very small at these two endpoints. It should probably increase, and in the center near n by 2, it should take the maximum value or something like that. In expectation, however, the length of longest increasing subsequence, we will see, is closer to square root n. Okay, it's 2 square root n in some precise sense. So that's something that we will try to prove throughout this talk. Okay, so for simplicity, let me also make a notation. This probability that length of longest increasing subsequence is equal to k, I'll just call these numbers p and k, little p and k. Okay, so notice, for example, in our very simple example of this parity, the sign of the permutation, we exactly determined the distribution of the sign of sigma, and we said that it's Rademacher random variable. So in this example, again, you might be brave and you might say, basically, can I determine, for example, the distribution of L sigma n? What is this? And this is basically same as showing this. Can we basically determine, can we understand, can we determine the sequence p and k, this number? Okay, so we have already determined p and k at these two extreme endpoints, right? And this question before, okay, I'll come back to this question maybe towards end, but let me briefly mention that there is a related question to this, which is still open, and it's one of very prominent and important problem in this field. But let's get back to this. Since we don't have an exact distribution of L sigma n, can we at least get some idea about what expected value of L sigma n is? So this is our question. And as an aside, so what we are going to do in this talk is that we will see that the expected value of L sigma n, this is greater than or equal to root n, and we will also show that the expected value of L sigma n, this is less than, I don't know, we'll see what the proof gives us, but let's say something like 10 root n. Okay, So the 10 might be 2, it might be 500, I don't know, we'll see in the proof. But the point here that I'm trying to make is that the expected value of L sigma n is of the order square root n. More precise or honest theorems are the following, that the expected value of L sigma n, if you divide it by square root n, this converges to 2 as n goes to infinity. So this we will not be able to prove in this talk, but this is something that you should keep in mind, and this is kind of close, that we are basically saying that if at all you have to divide it by something and take the limit, root n is the right quantity by which you should divide. Whether the limit exists or it doesn't exist, what is the limit, those remain the final question. Okay, so this came through like a sequence of work on this similar topic by Logan and Shep, Varshik and Kero, and I think Dive and Johansson. And then there is also on this particular topic somewhat stronger result. I think Elders and Diaconis has a paper. Okay, so if you are more interested in this topic, you should check out these papers. Before I go to the proof, let me also mention one more reference here, that there is a beautiful book by Dan Romick, and the title of the book is The Surprising Mathematics of Longest Increasing Subsequence. So the first chapter, I believe, is pretty much readable. Then soon the material becomes very technical, because this simple question, as you see, for example, we haven't done anything terribly complicated. We all understand permutations. This can seem like a game. Let's just count what is the longest increasing subsequence that you can get, and trying to understand its behavior. It relates to number theory, it relates to representation theory, it relates to random matrix theory, and so on. So there is so much material on just this one particular statistic, just the longest increasing subsequence, that there is a book about it. So if you are interested, you should read. Now let's go back to our question and try to prove these two results. So first, let's try and prove that the expected value of L sigma n is less than, let's say, 10 root n. Okay. And once again, I emphasize that we might have to revise this 10 later on, but we will see. So how do you do that? The idea is that we will first estimate what is the probability that there is a subsequence, or the longest increasing subsequence has length greater than equal to k. Okay. Now imagine you have a permutation in which the longest increasing subsequence has length at least k. This is same as basically saying the probability that there exists some subsequence or some increasing subsequence of length greater than equal to k. All right. So far we haven't done anything terribly important, but now I'm going to use the union bound. I want basically some I1, I2, Ik that are increasing. And I also want the sigma I1, sigma I2, sigma Ik, these to be in the increasing order. So what I do is that I first choose k many numbers, I1, I2, I3, Ik, for where I actually want to see this increasing subsequence. There are n many total numbers that I have. So I can choose k many of those in n choose k many ways. And once I have picked this collection, let's say I1, I2, I3, Ik, there are factorial k many ways these could have been actually appeared in a random permutation. But out of those, there is exactly one in which they appear in the increasing order, right? So there is a 1 over k factorial chance that I1, I2, I3, Ik appears in exactly that increasing order. So since this is a union bound, we get a less than or equal to. So the probability that the longest increasing subsequence has length bigger than k is at most n choose k over factorial k. Okay. Now this quantity, let's write it as factorial n. Okay. So let's write it as 1 over factorial k square and factorial n over n minus k factorial, right? Which is less than or equal to n to the power k over factorial k square. Okay, let me explain this one a little bit. I haven't done anything really complicated here. Factorial n is, or factorial n over n minus k factorial, this quantity is just n times n minus 1 times n minus 2 times n minus k plus 1, right? Each one of these product terms are actually less than n, and there are k many of those. So I'm basically bounding this by n to the power k. Okay, so I hope that this inequality is clear to everybody. So great. Let's put it in a box. This will be important. This estimate that we have, this works for every k. So now what we are going to do is that we will take, or let's make one more simplification to get some idea of what k we should actually choose. Is everybody aware of Stirling's approximation? So I need a very weak version of Stirling's approximation. What I need is that factorial k is actually bigger than k over e to the power k. Okay, so take this as a fact, not too hard to prove. What it is basically saying is that factorial k, there is basically k minus 1, k minus 2. So it's obviously less than k to the power k, but it's more or less, if you divide k by just a constant, then it is actually like k by e to the power k. There is a more precise version of this, but we don't need that. Okay, so if you accept this, then we get that probability that longest increasing subsequence has length bigger than k. This is less than n to the power k over k to the power 2k e to the power 2k, which I'll write as e times a square root n by k raised to power 2k, right? Now, what does it tell us? The probability that L of sigma n is greater than or equal to, notice that if this k, I choose something like 2e root n, then e root n divided by k will be like half, and then I'll get something like half to the power k. So the length of longest increasing subsequence actually exceeds 2e times a square root n, is at most 1 over 2 to the power k, in fact 2k, and k in our case is 2e root n, so we get something like 4e root n. Okay, so these numbers are not terribly important for us, so I'll just write it as delta to the power root n. The thing that matters to us is that delta is actually less than 1. Okay, so what is this telling us? This is telling us that you get a longest increasing subsequence of length much larger than root n that has a probability that decays exponentially. It goes to 0 very fast. Okay, and this allows you to basically compute the expectation, the expected value of L sigma n. This you can write, let's write it like this: k times the probability that L of sigma n is equal to k. This is just a formula. And this sum we will break into two parts. So we will sum it from 1 to 2e root n, if you want 2e root n minus 1. Plus when k is bigger than 2e root n. Okay. So now for this first part, what I'm going to do is that I'm going to pull out this k. K can be at most 2e root n. So let's just pull out a 2e root n. And then I sum over all these probabilities. When I sum over all this probability, I get a probability that L of sigma n is less than or equal to 2e root n minus 1. Which is, by the way, is a probability, and therefore it's less than 1. So I'll just drop this term as well. So this first term is smaller than this quantity. Plus, for this second term, I do the same trick. K can be at most n, so I pull that out. And now if I sum over these probabilities that the length of sigma n is equal to k, but then k is running from 2e root n to n, this is same as the probability that L of sigma n is bigger than 2e root n. But this probability we already know is like delta to the power n. So I'll replace this by delta to the power n. Sorry, delta to the power root n. You exactly know what delta is. I'll not do that computation, but it's okay. So we got the expectation. We got the expectation. It's actually 2e root n plus n times delta root n. So to get my claim like 10 or 20 or 50, all you have to basically show is that n times delta root n is actually smaller than, let's say, e root n. If you could show that, then this whole sum I can write less than 3e root n. Okay. Now this quantity, as you can see, for example, n times delta root n, the fact that delta is like 1 over 16 to the power e and so on, this actually goes to 0 as n goes to infinity. So if not e root n, if you just choose your constant c large enough, then this is less than c times root n, but you can in fact show that it's much smaller. So this gives you this bound. Okay. So this 3 might be 30, we don't care. So I hope this is clear. Let me sort of summarize this whole idea. The summary is that we want to prove some bound like this. We first found an estimate on the probability that you get to see a long subsequence. And we basically showed that that becomes very unlikely the moment you cross a threshold of something like root n. The right threshold is, let's say, e root n. So you can't quite cross the 1 plus epsilon times e root n threshold. The probability starts decreasing very fast at that rate. And therefore, you get the summation. Okay. So modulo this one probability estimate, which also is actually a very simple estimate. There is nothing really non-trivial here. The non-triviality of this problem, it becomes really interesting and non-trivial problem when you actually try to pin it down precisely how much it is. So, and we know by now very precise estimate on length of longest increasing subsequence. As I said, for example, here, you know that as n goes to infinity, it's 2, but we know something more, for example. So let me, as an aside, add here that length of longest increasing subsequence, this we know is like 2 root n plus, it's actually slightly bigger. There is some constant times n to the power 1 over 6. We actually know what this constant is. Plus, there is some error term, which is much smaller than n to the power 1 over 6. Great. I guess I have only 10-15 minutes. So I'll quickly give you a sketch of the other side of this inequality, meaning the expected value of L sigma n is less than equal to root n.
Sorry to interrupt. There is someone is asking
Yes.
a question in the chat. Anhat Jha. He's asking, can
Yes.
you just go over how you decompose the sum and what followed after that?
Okay, sure. Yes. So let's go from here. So this first equality is the definition of the expected value of L sigma. L sigma can take values from 1 to n. So I have k times the probability that L sigma takes the value k. All I'm using here is that the expectation of a random variable x, this is sum running from 0 to infinity. k times the probability that x is equal to k. Okay. Now this sum k runs from 1 to n. So I basically split this very same sum into k running from 1 to 2e root n minus 1 and k running from 2e root n to n. So I have not done really anything here. In this splitting, this is exactly the same sum. It's just written in two parts. Why do I write it into two parts? The reason for that is that I have a probability estimate from here. And this probability estimate, I know that it starts decaying very fast. So it's much more controllable if I sum things over 2e root n. Okay. So I want a sum from 2e root n. This is a standard technique. You can think of it as if there is a good part and there is a bad part. The good part is where this probability decays very fast. So we decompose this sum into the good part, good case, where k is very large, but the probability is actually very small. The second part is where k is actually small, but the probabilities we have no control over. The probabilities can actually be very large. So this is this second equality. Now in this equality, let me actually delete these terms. I went a bit fast over this, but here for this first sum, what is the largest value k can take? K can take at most this value 2e root n minus 1. I'll not write that. So there is 2e root n times you will still get a sum k running from 1 to 2e root n minus 1 probability that L of sigma n is equal to k. And plus, similarly here, the largest value k can take in this sum is actually n, because k is at least as big as 2e root n, but it can go on only till n. And then you have sum k running from 2e root n to n, the probability that L sigma n is equal to k. So this step I sort of didn't write previously. But now what you can do is that you can look at this whole sum. The probability that L sigma n is equal to 1 plus probability that L sigma n is equal to 2 plus probability that L sigma n is 2e root n minus 1. If you sum all this probability, this is same as the probability that L sigma n is between 1 and 2e root n minus 1. So this is probability that L sigma n is less than 2e root n. Times, obviously, you had this 2e root n. And you play the same trick here. There is an n. And if you look at this sum, then this is the probability that L sigma n is greater than equal to 2e root n. It is between 2e root n and n. So these were the two steps that I did not write. And at this step, this probability we don't really have a control on. But then it is a probability, so it's at most 1. So we ignore this. This quantity we say is less than 2e root n. Plus, this time I have an n. Notice n can be very bad for us. It can be disastrous. We only want this thing to be of the order square root n, and we already see an n here. So what we want is that this term we want to compensate for this n. So this we want to be actually decaying to 0, and we want it to go to 0 at least like 1 over square root n. But then we have a precise control on this. This one we have derived, and this one was delta to the power square root n. So this was the estimate that I got. You can just leave it at that. If you want to go more, then you can actually compute that this n times delta root n is also less than, let's say, e root n or something. Okay. So, okay, I hope that was clear. I'll rather stop for some questions answers at the end. So I'll not do the proof of this part, the expected value of L sigma n less than equal to root n. But let me actually give a sketch because it involves one very beautiful idea. So you need a lemma. This is a cute lemma. You should take it as an exercise. You should try to do this proof that suppose you have sigma in Sn. This need not be random. Just take any permutation sigma in Sn, and n is bigger than, let's say, r times s for some numbers, for some r and s in natural numbers. So for example, when n is equal to 10, you can take your r is equal to 2, s is equal to 5. You can take r is equal to 3. Okay, let's take it 11, and s is equal to 3, and so on. So for any such R and S, as long as you can write n bigger than R times S, then the conclusion is there is either an increasing subsequence in sigma of length R, or there is a decreasing subsequence in sigma of length S. So what it says is that you can't really have a permutation where there is no increasing subsequence. The length of longest increasing subsequence is also small and the decreasing subsequence is also small. So if you notice that you can make one of them very small, we already saw that there is a permutation in which the increasing subsequence has length 1. But then in that permutation, you will actually get a decreasing subsequence, which is very, very huge. It has length n. So these two kind of compensate for each other. And with this, I can give you the proof. The proof is that we are interested in the longest increasing subsequence in ln, the sigma n. This, first of all, you need to observe that the length of longest increasing subsequence and the length of longest decreasing subsequence, they have the same distribution. Okay. Why is that? Basically every time you get a subsequence, get a permutation which has a longest increasing subsequence of some length, you can actually reverse the digits. You can start reading them in the opposite order, and you will actually get a permutation which has a decreasing subsequence of the exactly same length. So they have the same averages. So this is the first equality. I'm not going to explain this a lot, but once you are convinced of that, you use what is called the AMGM inequality, arithmetic mean geometric mean, which tells you that this quantity is at least square root of L sigma n times D sigma n, right? And this lemma that we just wrote, this lemma basically tells you that the product of L sigma n and D sigma n is always at least n in any permutation. So you get the expectation of a square root n, which is just a square root n. So this is the proof. I went over it a little too fast, so don't worry if you didn't quite get it. Let me make some final remarks. So one question that I left somewhere here, and I said I'll come back to this, that this whole argument was only understanding the expected value of L sigma n. But you might ask a question about what is the distribution of L sigma n. In other words, you might be interested in just understanding this sequence of numbers, this probability that the length of longest increasing subsequence is equal to k. So let me redefine that term here. Pnk is the probability that a uniform random permutation sigma in Sn has L sigma n, meaning a longest increasing subsequence has length k. Okay, just for the completeness, this is the number of permutations sigma in Sn for which the longest increasing subsequence has length k, and you divide it by factorial n. Okay, this is still an open conjecture, and this I think might be wrong about date, but William Chen conjectured, I think in around 2006 or 4, that this sequence of numbers p and k, they satisfy an inequality, namely this. Okay. So this has a technical name. This is called log concavity. So in fancy jargons, we will say that P and K is log concave. What it essentially means is that the square of P and K is bigger than the product of P and K minus 1, P and K plus 1. If you want a pictorial representation, basically if you plot these numbers from 1 up to n, what it means is that you see some shape which looks like this. Okay, this is how your P and K would look like. it will have a peak, and then it will start decreasing. And that peak, we obviously know already that it should be somewhere in a window around square root n. Okay. To give some example of this, let's conclude with this last example. If you look at S3, K can take only three values, 1, 2, and 3. And how many permutations are there in Sn for which the longest increasing subsequence has length K? We have already seen that there is only one for which the longest increasing subsequence has length 1. There is exactly one permutation for which the longest increasing subsequence has length 3. There are total 6 permutations. So there are 4 permutations which have longest increasing subsequence is equal to 2. You can check this. For example, 4 square is greater than or equal to 1 times 1. If you do this for S4, do this exercise again. I'll lead this to you. We already know the number here is 1 and 1. I mean, if you want, you could have divided it by the 3 factorial, which is 6, but would not matter because you have a 1 over 6 at each of these places. So we already know these numbers, 1 and 1. How many permutations in S4 have longest increasing subsequence of length 3, longest increasing subsequence of length 2? I'll leave it to you to check that these numbers are 10 and 12. So you can again verify the log concavity. 10 square is bigger than 1 times 12. 12 square is bigger than 10 times 1, and so on. So this has been verified for, I think, maybe till n is equal to 20 or so. The conjecture as of now remains open. There is a recent work, if you are interested, on some variant of this. Instead of studying these numbers P and K, you can study some Poissonized version of this. And many of you would have already attended the talk of Professor Manjunath Krishnapur on day 1. And he and Gyaneshwar, who is a student at ISC, and Professor Manjunath with Moksha Mariman, they have a recent paper where they studied this problem, this log concavity problem. This problem, as I'm saying, is still unsolved. It remains open. They study some variant of this problem, and they show that if you Poissonize this, whatever that means, then you do get log concavity, and it leads to some interesting results in that direction. But this problem, as of now, still remains open. So the reason I am mentioning this is to emphasize that permutations are classical objects, we all understand, and there are many properties associated with them. As we wrote initially, there is a sign, there is an order, there is longest increasing subsequence. You can ask how many bits I need to flip, the smallest number of bits that or smallest number of transpositions I need to apply so that I can convert it to the identity. And you can ask the number of cycles. Any of these questions, if you start asking it about the random permutations, all of these lead to very, very interesting mathematics. And we just saw one very specific particular example of this. And many of these problems have been studied for a very long time, and they contributed to very rich body of mathematics. Many of these problems are still open. Many of these problems are still being worked on. So this is to emphasize, if you just play around, if you just start playing around the things that you are learning in your classroom, there is a lot of interesting mathematics that you very naturally can reach to. So I hope that some of you will like this topic, pursue it further. Maybe one of you will solve the Chin's conjecture someday. Okay, so I'll stop here and I'll wait for the questions if you have any. And I'll maybe stop sharing if that's okay.
If anyone has a question, please ask.
So, what about the variance? Like, do we have?
Yes, so the variance in this case turns out to be of the order the variance of L sigma n. This is of the order n to the power 1/3. So this asymptotic that I wrote somewhere, that the length of longest increasing subsequence in fact is 2 root n plus n to the power 1/6. This comes from that that variance computation, and there is a reason why this happens. I mean, this n to the power 1/3, people those who work with the KPZ and those kind of things, they will recognize where this exponent is coming from. So it belongs to a certain universality class, and the fact that this n to the power 1/3 pops up here is because of that. So yeah, we in fact have precise limiting distribution. So L of sigma n minus let's say 2 root n by n to the power 1/6. This converges to the Tracy Vidam. So this is also known, but the proof of this involves its connection with the connections with the rightmost eigenvalue of GU ensemble and so on. So in this work of Yaneshwar, Manjunath, and Moksha, they also prove, for example, the lock concavity of the Tracy Vidam 2, which was not known in its full generality. So
Okay.
Okay, then we'll
okay.
finish this meeting here. Thank you, Raghavendra, for being with us. And for the participants, I'll remind you again that the next meeting is from 2. Okay, so bye.
Okay. Bye bye.
Thank you. Bye. Can you please stop recording?